It's a quiet evening, and I'm glad you found your way here. Welcome back to The Lazy Scientist. Before we begin tonight's journey, I want you to take a breath, let your shoulders fall, and let the noise of the day fade into the background. If you're new here, I'm glad you joined. A gentle tap on the like button or a quiet little subscribe helps more wandering minds drift into this space. And if you've already been part of this slow voyage, thank you. Your support is what keeps these whispered explorations alive. I truly hope tonight's story soothes you toward rest, but if you find yourself too interested to fall asleep, at least you'll have something wonderful to ponder as you wait for your mind to slow. Tonight, I want to lead you into a question so immense it bends at the edges. Can we ever really understand how vast the universe is? We throw around the word big casually. A big tree, a big meal, a big city. Sometimes we even exaggerate and call something huge or massive. But when we turn our gaze upward, toward the cosmos, those everyday words become flimsy. They fold in on themselves. Compared to what's out there, even our most dramatic descriptions barely touch the surface. Our brains weren't carved by evolution to wrestle with galactic scales. We learned to judge the distance to the next branch in the forest, or how far away a predator lurked. We can measure a road in kilometers or miles, and that feels natural. That's the scale we're comfortable with. A walk across the street, a trip to another town, a flight across the sea. But the moment we push beyond the boundaries of Earth, the language of distance begins to break apart. What waits out there doesn't just stretch the imagination. It teases it, laughs at it, and leaves us standing in awe. So let's drift outward together. Imagine this as a guided float into immensity, where numbers become metaphors and distance becomes poetry. We'll start from the ground beneath your feet and move slowly, step by step, until we find ourselves at the edge of the known cosmos. This isn't a lesson in memorization. It's not a test. Think of it instead as a meditation on scale, a way to sit with the unthinkable and let it wash over you. Because sometimes the most human thing we can do isn't to solve the riddle of the universe, but simply to marvel that we get to wonder about it at all. When you think of distance, what comes to mind? Perhaps the block you walk to grab a coffee, the drive to visit family, the flight that crosses oceans and leaves you jet-lagged. These are scales we know because we felt them. We've measured them with our legs, our wheels, our hours. A meter, a kilometer, numbers you can picture, steps you can count. But take one step beyond Earth, and the measurements collapse. Our rulers, our yardsticks, our habits, they're laughably inadequate. It's like trying to measure the Pacific Ocean with a teaspoon. You can do it in theory, but the task itself mocks you. Let's begin with something familiar, the moon. That pale coin in the night sky is about 384,000 kilometers away. It sounds impossibly far, and yet it's still close enough for human intuition to grasp. It's the distance you'd cover if you flew around Earth nearly 10 times. Manageable, at least in imagination. Now look farther. The sun, our great fire, our daily companion. About 150 million kilometers stand between us and it. Sunlight, moving at the fastest speed anything in this universe can travel, takes over 8 minutes to reach Earth. That number is so central to astronomy, it has its own name. 1 astronomical unit. We use it as a yardstick inside our solar system. Mercury whirls around the sun at about 0.4 AU. Jupiter drifts at 5.2 AU. Neptune, that cold outer world, at nearly 30. Astronomical units shrink impossible distances into something our minds can at least pretend to chew on. But the moment you step outside the solar system, even those units disintegrate. The nearest star beyond our Sun is Proxima Centauri, a faint red dwarf. Its distance, just over 4 light-years. In astronomical units, that's 268,000. Try fitting that in your head. It's like trying to keep track of grains of sand, one handful at a time. So astronomers switch tools. They use the light year. A light year isn't time, it's distance. It's how far light, that relentless traveler, moves in a vacuum in a single year. At 300,000 kilometers per second, light racks up mileage quickly, nearly 10 trillion kilometers in just 1 year. 1 light year. When we say Proxima Centauri is a little over 4 light years away, we're saying the photons we see from it tonight began their journey more than 4 years ago. If it exploded right now, don't worry, it won't. We wouldn't know until years in the future. A light year is a ruler, but it's also a time machine. Every glance at the night sky is a glance into the past. The farther out we look, the older the light. Every star we see is history replaying itself in silence. It's not space as it is, it's space as it was. A telescope is not just an eye, it's a clock that runs backward. Astronomers have caught galaxies glowing from more than 13 billion years ago. Imagine that. We're watching faint embers from a universe still in its infancy, long before Earth, before the Sun, before anything we know. For those who love math, there's another unit, the parsec. About 3.26 light-years. It's based on how nearby stars seem to shift against the background as Earth loops around the Sun. It's a beautiful piece of trigonometry. Useful, yes, but for most of us, light-years feel more intuitive, more poetic. Still, no matter what ruler we reach for, kilometers, AU, light-years, parsecs, the result is the same. The numbers balloon until they slip through our fingers like water. They become too large to mean anything. Our minds evolved to deal with horizons a few miles away, not gulfs spanning billions of years. That's why figures like 100,000 light-years, the width of our galaxy, or 13.8 billion light-years, the age of the observable universe, feel more like poetry than mathematics. But here's the magic. These numbers, these rulers, they stretch us. They bend the limits of our perception, pulling our thoughts just a little closer to the stars. They may not bring the universe down to our size, but they allow us to rise a little, just enough to brush the edge of immensity. And at the heart of all of this is a law, a speed, a boundary written into the fabric of reality, the speed of light. In the great silent courtroom of physics, the speed of light is the final judgment, just under 300,000 kilometers per second, fast enough to loop Earth 7 times in 1 second. The ultimate limit. No matter your engines, your determination, your imagination, you cannot outrun light. Einstein's famous equation, E=mc², leans on it. The c in that formula is the speed of light itself. It's not just a measurement. It's woven into the structure of reality. Because light is so fast, so steady, we use it to measure the cosmos. But in doing so, something remarkable happens. Space and time, which we normally think of as separate, begin to blur. In everyday life, you can measure distance and duration separately. A walk might be 5 kilometers and take an hour. A drive might be the same distance, but take 5 minutes. Distance and time are flexible partners. But in the cosmos, those lines collapse. When we say something is 1 light year away, we're saying 2 things at once: how far it is, and how long ago the light began its journey. Every measurement is also a timestamp. This is where light begins to play tricks with our sense of time. Look at the moon, and you're seeing it as it was a little over 1 second ago. Look at the sun, and you're seeing it as it was 8 minutes ago. The warmth on your face is the sun's farewell, sent minutes earlier while you were still brushing your teeth. Look at Sirius. the brightest star in our night sky, and you're seeing light that set out 8.5 years ago. Look at Andromeda, our neighboring galaxy, and the light has been traveling for 2.5 million years, long before humans walked upright. The night sky isn't a present moment. It's a museum of ancient postcards. Every star you see, every faint smudge, is a message delayed. Space doesn't allow us the luxury of now. The present exists only for what is near. The farther we look, the older the show. And telescopes, those patient instruments, are time machines. They don't just reveal distance, they reveal age. The farther they reach, the deeper into history they peer. Some galaxies we observe sent their light before the Earth itself existed. That is the gift of light speed. It doesn't just connect us across space, it stitches us across time. Imagine this. If the sun were to vanish, gone in an instant, snuffed like a candle, we would still see its light for 8 minutes. The sky would stay bright. Earth would go on, unaware, because the last photons were already en route, carrying the illusion of permanence. We live in delay. Our eyes don't see the present, they see the past, always. This has strange consequences. In the realm of relativity, simultaneity doesn't exist. There is no single now across the universe. Two observers, moving at different speeds or under different gravity, will disagree on what time it is. Light locks time to the observer. Everything is relative. For us, this is deeply unintuitive. We like our clocks to match. We like things to happen in order. But the cosmos doesn't care about our preferences. Time stretches and folds like a dream. And yet there's comfort in this strangeness. Because no matter what, the speed of light never changes. It doesn't falter. It doesn't grow weary. Wherever you are, however you move, you'll measure it the same. It's the universe's universal truth, a glowing thread that weaves every galaxy, every moment, into one continuous fabric. When you gaze up at the stars, remember this: you are not just looking into space. You are looking into memory. A billion flickering histories, twinkling across the dark. And whether their journeys lasted seconds or billions of years, they all obey the same patient, relentless pace. The speed of light doesn't just limit us, it connects us. It carries the stories of everything that ever shone. And tonight, some of those stories have found their way to you. If you were to ask someone how large the solar system is, they might imagine a tidy diagram from a textbook. The planets strung out neatly in a line. Mercury closest, Neptune farthest, each one a colorful bead circling the sun. It's an appealing picture, but also a deeply misleading one. What defines our solar system isn't the planets themselves. It's the emptiness that stretches between them. Start with the moon. Orbiting Earth at about 384,000 kilometers, it feels close enough to touch with your eyes. You can picture its glow, trace its face with your gaze, and even remember that human beings once walked upon its dust. In cosmic terms, it sits practically on our doorstep. Now think about the Earth-Sun distance, 150 million kilometers, 400 times farther than the moon. This distance is so iconic it earned its own shorthand, 1 astronomical unit. If you tried to drive that span at ordinary highway speeds, say 100 kilometers per hour, it would take more than 170 years of uninterrupted travel. Even the innermost planets quickly reveal how deceptive our scale of thinking is. Mercury is just a third of an astronomical unit from the Sun. Venus is 2/3. Earth is 1. Mars sits at 1.5. Then the gaps start widening. Jupiter waits beyond 5 AU. Saturn spins at nearly 10. Neptune orbits at more than 30. And in between, vast gulfs of nothing. To make this clearer, astronomers sometimes turn to analogy. Imagine shrinking the sun to the size of a basketball and setting it down at the center of a football field. Earth, on that scale, would be a tiny peppercorn about 25 meters away. Neptune, a small marble, would sit almost at the far end of the stadium. And the seats in between? Empty. That's the reality of our solar system. It isn't a bustling neighborhood of worlds jostling together. It's a desert of silence, punctuated only by occasional oases. Even the asteroid belt, which movies often portray as a crowded junkyard of rocks, is mostly nothing. If you stood on one of its bodies, chances are you'd see no neighbors at all. Perhaps a faint dot glimmering in the distance, perhaps nothing. The truth is, space is generous with distance and stingy with matter. And still, Neptune is not the end. Beyond the orbits of the familiar planets lies the Kuiper Belt, a wide band of icy debris that stretches from about 30 to 50 astronomical units. This is Pluto's realm, along with other small frozen worlds, Eris, Haumea, Makemake, distant objects tracing slow orbits in the twilight. Beyond that, farther still, lies a region so remote we've never seen it directly, the Oort cloud, a vast spherical shell of icy bodies, extending perhaps 100,000 AU from the Sun. That's more than 1.5 light years. Imagine that. The Sun's gravitational influence may reach halfway to the nearest star, and even then, it dwindles into weakness and distance. Consider Voyager 1, humanity's farthest traveler. Launched in the late 1970s, it has been moving steadily outward for over 4 decades. Today, it sits more than 150 AU from the Sun, farther than any other human-made object has ever gone. And yet, it hasn't even touched the Oort cloud. At its present pace, it won't arrive there for centuries. To cross it fully might take tens of thousands of years. Voyager is our message in a bottle, a tiny emissary of Earth adrift on an endless ocean. Its golden record carries our greetings, our music, our images, a fragile reminder of how far we've reached and how far we have yet to go. And here's the humbling truth. All of this, the planets, the moons, the belts, the comets, the probes, still sits in the immediate neighborhood of our Sun. Our solar system, for all its enormity, is just a tiny bubble around a single star, and our galaxy is filled with hundreds of billions more. That's when the scale slips entirely out of reach. The distances between stars are not measured in astronomical units anymore, not even in thousands. They are measured in light years, and even the nearest neighbor is daunting. Proxima Centauri lies just over 4 light years away. That's more than 40 trillion kilometers. Light itself, the universe's speed champion, needs more than 4 years to make the trip. Our fastest spacecraft would require tens of thousands of years. And beyond Proxima, beyond Alpha Centauri, stretch countless other stars, each farther still. Try another analogy. Imagine a flat field stretching kilometers in every direction. Place 1 grain of salt on the ground. That's the Sun. Now walk 8 kilometers away and place another grain. That's Proxima Centauri. Repeat the process over and over, and you'll begin to sense the reality of interstellar space. Stars scattered like lanterns across an immense fog, separated not by meters, but by lifetimes. Even when we think about the stars themselves, their scales defy us. Proxima is small and dim, yet still more than 100 times the mass of Earth. Our own Sun dwarfs us completely, over 300,000 times Earth's mass. Stars are enormous, blazing furnaces of fusion, yet scattered so sparsely that the Milky Way looks like a thin band of haze from our perspective. And this is the lesson the universe teaches again and again. The larger you zoom out, the emptier it becomes. Galaxies are not solid islands of light. They are swirls of stars separated by deserts of void. Clusters of galaxies stretch across millions of light years, but even they are strung together by filaments, separated by even larger emptiness. What we think of as the universe is mostly nothing, a lattice of vast gulfs stitched with rare sparks of light. And yet, this emptiness is not meaningless. In fact, it is what allows structure to exist at all. If the universe were tightly packed, stars and planets could never form, galaxies could never drift into being. The silence between things is not absence. It's space for rhythm, for orbits, for life. All of this returns us to the original thought. Can we really comprehend how big the universe is? Maybe not. Maybe our minds will always stumble, trying to leap across gulfs measured in light years and eons. But we can approach it with awe. We can stretch ourselves against the edge of understanding, even if we never grasp it fully. Because in the end, that might be the point. Not to reduce the cosmos to numbers, but to feel the weight of its mystery. To let the stars remind us how small we are, and at the same time, how lucky we are to wonder. Every glance at the night sky is not just an act of seeing, it's an act of remembering. The photons that strike your eye tonight have been traveling for years, centuries, millennia. They are whispers from ancient fires, reminders that we are connected not just to our world, but to a vast and timeless expanse. The cosmos doesn't ask us to understand it. It only asks us to notice, to look up, to pause, and to let the vastness wash over us. To feel, if only for a moment, the beauty of being small in a universe so immeasurably large. Even Neptune, icy and remote, isn't the end. Beyond that pale blue sentinel lies a dim frontier called the Kuiper Belt, a cold ring of debris stretching from about 30 to 50 astronomical units from the Sun. It's a frozen realm, a twilight region where small worlds drift silently. This is Pluto's home, joined by Eris, Haumea, Makemake, and countless other icy fragments. They are not planets in the familiar sense, but they trace their lonely paths like sparks caught at the edge of the fire's glow. And still the solar system continues outward, farther than most of us can picture. Beyond the Kuiper Belt, in a realm almost mythical, astronomers imagine the Oort cloud. We've never seen it directly. No telescope has resolved its edges, yet all the evidence suggests it is there, a vast spherical shell of icy bodies surrounding everything we know. It may extend nearly 100,000 astronomical units from the Sun. That's more than 1.5 light years. Think about that. The Sun's gravity might reach nearly halfway to the nearest star. But in those outermost regions, gravity is frail, objects are scattered, and time itself seems to slow. To sense this scale more clearly, consider Voyager. In the late 1970s, two spacecraft, Voyager 1 and Voyager 2, set out to tour the outer planets. Their cameras gave us our first close looks at Jupiter's storms, Saturn's rings, Uranus's pale tilt, and Neptune's dark winds. Then their grand tour ended, and they just kept going. Voyager 1 now drifts more than 150 AU from the Sun, the farthest human-made object ever built. It has been racing through space for nearly half a century, moving at over 60,000 kilometers per hour, and yet even after all this time, it has not reached the Oort cloud. It will take hundreds of years to get there, and tens of thousands more to pass through it entirely. Voyager is more than just a probe. It's our bottle tossed into the cosmic ocean. Tied to its hull is the golden record, a message etched with sounds, images, and music from Earth. Waves crashing, a child laughing, greetings in dozens of languages, a reminder that somewhere in a small corner of the galaxy, there was a species that dared to send its voice outward. Whether it is ever found doesn't matter. The gesture itself matters. It says, "We tried." And yet, here's the humbling truth. All of this, the planets, the moons, the belts, the comets, the probes, still exists only in the immediate neighborhood of the Sun. The solar system, vast as it seems, is just a fragile bubble around a single star, in a galaxy filled with hundreds of billions more. It's staggering to think that even within our own star's domain, the distances defy comprehension. And yet we've measured them, we've mapped them, we've hurled machines into the void to touch their edges. What defines the solar system isn't only the glowing furnace of the sun or the orbiting dance of the planets. It's also the emptiness between them, the silence that stretches endlessly, but even that silence has rhythm. Planets circle, comets return, light streams outward in all directions. Even in emptiness there is motion. So how big is the solar system really? It's as large as everything we've launched, everything we've glimpsed, and everything we still dream of reaching. And the more we travel, the more we realize we've barely begun. The sun feels eternal. Every morning it climbs above the horizon, warming our skin, marking the passage of days. Its permanence is an illusion, but a comforting one. Yet when we turn our eyes toward the next nearest stars, the comfort evaporates. Suddenly the universe stretches into silence so vast it shakes the mind. The closest star system to ours is Alpha Centauri. It's a family of 3 suns bound by gravity. Alpha Centauri A and B, 2 stars much like our own, and Proxima Centauri, a faint red dwarf that orbits at a far greater distance. Proxima is the nearest of them, and therefore the nearest star to Earth. But nearest is deceptive. It lies more than 4 light-years away, over 40 trillion kilometers. Numbers like that slide off the brain. 4 light-years might sound small, especially after hearing about billions, but pause for a moment. Light, the fastest thing in the universe, takes more than 4 years to cross that gulf. Voyager 1, traveling outward at its steady 60,000 kilometers per hour, would need more than 70,000 years to arrive, and that's just to the very nearest star. To help picture it, scale things down, shrink the sun to the size of a marble. Place Earth a meter away as a speck of dust. Neptune would sit 30 meters out, near the far end of a hallway. And Proxima Centauri? On this scale, it would be another marble over 8 kilometers away. And between them, nothing but empty air. That is the scale of interstellar space. It's not the stars that are the challenge. It's the yawning gaps between them. This is why interstellar travel feels so daunting. It's not the stars themselves that taunt us. It's the space between. Our fastest rockets struggle even to cross the solar system. The leap to another star is of an entirely different order. We'd need engines unlike anything we've ever built, power sources not yet imagined, and patience that spans centuries. Science fiction skips these gulfs with ease. Warp drives, hyperspace, wormholes. With a twist of narrative, entire galaxies become neighborhoods. But reality has no shortcuts, not yet. We haven't sent a single probe to another star system, not one. Still, there are ideas. The Breakthrough Starshot project imagines sending tiny spacecraft, no bigger than chips, launched by powerful Earth-based lasers. If it worked, those minuscule craft could reach 20% the speed of light, racing to Alpha Centauri in just over 20 years. The concept is thrilling, but building and aiming something so small, with such precision, at such speed, remains firmly in the realm of theory. The engineering challenges are staggering, but the fact that we're even thinking about it, that counts for something. Because here's the truth. The universe is mostly nothing. Stars are not strung together like pearls on a necklace. They are scattered lanterns, each separated by gulfs of darkness. Our galaxy contains hundreds of billions of suns, yet on average, each one is about 5 light-years from its neighbors. That's 5 years of light speed travel between every point of light. Imagine how much darker the universe would be if even a fraction of those stars didn't shine. So let's try another analogy. Picture yourself standing in an endless field, kilometers wide. Place 1 grain of salt on the ground to represent the sun. Then walk 8 kilometers and place another grain to represent Proxima Centauri. Walk again and again. scattering grains in all directions. Slowly you'd build a model of the galaxy, a sea of emptiness peppered with specks, a galaxy of salt floating in silence. And even those grains, the stars themselves, are staggering in size and power. Proxima Centauri, by stellar standards, is small and faint, yet it still weighs more than 100 times the mass of Earth. Our Sun, by comparison, is more than 300,000 times Earth's mass. Each star is a furnace, a roaring sphere of fusion burning steadily for billions of years. And yet, despite their brilliance, they remain tiny points against the immensity of the void. The emptiness between stars is not just a matter of space, it's also a matter of energy and time. To cross those distances requires more than motion. It requires survival in the void. It demands protection against radiation, navigation across centuries, communication that doesn't fade into silence. And even if you arrived, there is no promise of a welcoming world. Many stars may host nothing but barren rocks, searing giants, or storms of gas. That is why astronomers study exoplanets with such care. We want to know which stars might host another Earth, another place where life could thrive. Because even if we cannot yet travel between stars with rockets, we can reach them with imagination. We can measure them, model them, dream about them. In thought, the stars are already part of us, already stitched into our story. That is the strange duality of space, unreachable by hand, but never out of reach for the mind. Even now, photons from Proxima Centauri, dim and red, are slipping into our sky, arriving as quiet whispers after more than 4 years of travel. They remind us that while the universe may be mostly empty, it is never truly silent. Somewhere across the gulf, other fires burn. Be mostly empty, it is never truly silent. Somewhere across the gulf, other fires burn. Lift your eyes on a clear night, and you'll see a faint milky band stretched across the sky. That ghostly ribbon is the Milky Way itself, our home galaxy. To the naked eye, it looks like a pale cloud, too smooth to resolve into stars. But in truth, it is made of hundreds of billions of them, all bound together by gravity, spiraling slowly in a cosmic whirlpool. The Milky Way is vast beyond easy description. Imagine a disk more than 100,000 light-years across, but only about 1,000 light-years thick in the main plane. Flattened, elegant, with a slight bulge in the center where the density of stars grows heavy. Even light, racing at 300,000 kilometers per second, needs 100,000 years to cross it from one edge to the other. That's the stage upon which our entire existence unfolds. Every human life, every civilization, every story has played out on a speck of dust orbiting one average star in this sprawling spiral. We are not near the center. We are not near the edge. Our solar system lives in one of the quieter suburbs, about 27,000 light-years from the galactic core, tucked into a minor spur called the Orion Arm. It's not a grand boulevard of stars, more of a side street nestled between two major spiral arms, Sagittarius on one side, Perseus on the other. In the grand architecture of the galaxy, we occupy no throne, no balcony, no center stage. But that anonymity is perhaps our greatest fortune. Here, away from the chaos of the core, stars are more spread out, planets have room to orbit undisturbed, life has time to take root, and yet we are never still. The entire solar system is being carried on a galactic current. Right now, our sun is hurtling around the center of the Milky Way at about 828,000 kilometers per hour. That's fast enough to lap Earth more than 20 times in a single hour. And still, at that speed, one full orbit takes staggering patience. A galactic year is about 225 million Earth years long. The last time the solar system was in this exact position, the first dinosaurs were just beginning to emerge. Since the sun was born about 4.6 billion years ago, it has circled the galaxy only about 20 times. 20 laps in billions of years. That is the scale of our cosmic track. What is most humbling is that from our perspective, the stars look frozen. A familiar constellation like Orion or Cassiopeia seems permanent. We draw myths into their shapes and imagine they've always been there. But nothing is truly still. If you could watch the sky in time-lapse, not over decades, but over millions of years, you would see stars drifting like fireflies in a dark meadow, weaving new shapes, forming and dissolving constellations in a slow, graceful dance. Near the galactic center, the picture is very different. There, stars are packed close together, swarming at incredible speeds around a dark and powerful anchor. Sagittarius A star, a supermassive black hole. It weighs as much as 4 million suns. We cannot see it directly, but we know it's there. Stars whip around it in tight orbits, some completing a circuit in just a few years, drawn by an invisible grip. It is quiet, but not passive. It is the gravitational heart of the Milky Way. Out here, far from that chaos, we drift in peace. The Orion arm is sparse compared to the core. That sparseness is our shelter. Without it, Earth may never have had the stability to nurture life over billions of years. Our neighborhood might not be glamorous, but it is safe, and that safety is precious. What's even more remarkable is how little of the galaxy we can actually see with our eyes. Every star you've ever looked at unaided, every twinkle, every wish, is within just a few thousand light years. That's a tiny fraction of the Milky Way's total breadth. The overwhelming majority of its stars are invisible to us, hidden by distance or veiled by interstellar dust. Radio telescopes, infrared surveys, and patient mapping have helped us outline the spiral arms, but to the naked eye, we see only the nearest members of our galactic family. It's tempting to think of the Milky Way as just a backdrop, a pretty stretch of sky behind our lives. But it is more than scenery. It is our island in the cosmic ocean, the only galaxy we've ever known from within. Every sunrise, every poem, every whispered secret has unfolded here on a small rock circling an ordinary star inside one unremarkable arm of this colossal structure. And we are still moving, still orbiting, still drifting with it. The night may seem calm, but you are, at this very moment, riding through the galaxy at unimaginable speed, on a voyage that began billions of years ago and shows no sign of ending. When we gaze at the stars, we might think of them as lonely points, scattered at random across the sky. But stars are not always solitary. They are often born in groups, cradled by the same clouds of gas and dust, bound by gravity and shared origin. These families of stars come in many shapes, and each type tells a story about the galaxy and the lives of suns. There are open clusters, loose associations of a few hundred or a few thousand stars, young and bright. They are stellar siblings, just recently emerged from their nursery clouds, still glowing blue with youth. They have not had time to drift apart. Their gravity binds them lightly, like children holding hands. One of the most famous is the Pleiades, also known as the Seven Sisters. On a clear night, you can spot them without a telescope, a glittering knot of stars in Taurus. The Pleiades are only about 100 million years old, infants by cosmic standards. They shimmer in the sky as a reminder that stars, like people, are often born together before they drift into their separate lives. Then there are globular clusters, the ancient elders of the galaxy. Unlike the loose open clusters, globulars are dense, spherical gatherings of hundreds of thousands, even millions of stars. They are ancient, some older than 12 billion years, nearly as old as the Milky Way itself. They swarm around the galaxy, like bees around a hive. orbiting not in the disk, but in a vast halo outside it. Viewed through a telescope, they look like dazzling spheres of light, stars so tightly packed that thousands fit in a single frame. One of the most famous is M13, the Great Hercules Cluster. It is a ball of ancient suns that have been glowing since long before Earth was formed, a cosmic time capsule of the earliest eras. Clusters remind us that stars, like people, have families and communities, and that even in the grand loneliness of space, there are bonds, connections, and shared origins. You would live beneath a sky that never truly darkens. Imagine standing on a world inside a dense star cluster, where the night is a layered blaze of starlight and the constellations refuse to hold still. A typical globular cluster can sit more than 25,000 light-years away and pack hundreds of thousands of suns into a sphere only a few dozen light-years wide. If you were there, shadows would be softer, horizons stranger, and the familiar sense of cosmic solitude would give way to a crowded, sparkling neighborhood where gravity speaks in a chorus. Beyond such clusters, the galaxy softens into haze. Those pale, colored clouds you see in long exposures are nebulae, which is simply Latin for cloud. That is exactly what they are, immense clouds of gas and dust that can span dozens or even hundreds of light years. In them, matter is patient and fertile. Hydrogen cools, dust drifts, shock waves rattle old bones of star formation, and pockets of gas collapse toward ignition. Some nebulae are the cradles of stars that have not yet learned their names. Others are the ashes of stars that have already spoken their last. The light is a record of both beginnings and endings. The Orion Nebula is the archetype most of us meet first. You can point a small telescope toward Orion's sword and see its faint glow, a soft, milk-white breath in the dark. It lies roughly 1,300 light-years from here and belongs to a larger complex called the Orion Molecular Cloud. Inside, young stars are turning on like lanterns, heating and sculpting the gas around them until it shines. The reds, blues, and violets you see in photos are not paint. They are atoms excited by newborn light, radiating gently from a nursery where gravity is doing its slow, inevitable work. Then there is the Eagle Nebula, famous for the pillars of creation. Those towering columns, seen so clearly in the Hubble images that traveled the world, are not small. Each pillar stretches several light-years in height. Within them, cold knots of dust and gas are collapsing, hidden from casual starlight. Deep inside, silent spheres are forming that will become stars, and around those stars, someday, there may be disks of rock and ice that learn to be planets. The image is beautiful because it is honest. It shows us that creation is not clean. It is sculpted from erosion and pressure, from wind and shadow, from time. Yet even these magnificent structures are tiny when set against the canvas that holds them. A grand nebula might span a few dozen light-years. A giant might reach a few hundred. The Milky Way disk is about 100,000 light-years wide. Place Orion's entire luminous cloud on a galactic map, and it shrinks to a thumbprint. Place a populous cluster next to the great spiral arms, and it dims to a fleck. From far away, the finest details become brushstrokes, and the brushstrokes become a suggestion. The lesson repeats. The closer we look, the more drama we find. The farther we drift, the more that drama resolves into texture. Within those delicate textures are entire histories. Stars are born, mature, and die. Planets form from the debris and learn to keep time with a parent star. Moons collide and settle. Atmospheres rise and vanish. Oceans appear where none had been, then sink back into stone. The quiet physics that shapes a nebula is the same set of rules that can make a shoreline and a tide pool. It is humbling to remember that the carbon in your breath was forged in the core of a star that once glowed like these, and that the calcium in your bones was lifted out of the dark by a chain of nuclear steps that began in clouds like these. Astronomers watch clusters in order to watch time. When you gather stars that share an age and a chemical fingerprint, you can line them up on a diagram and see how mass writes a life story. High-mass stars live quickly and die young. Low-mass stars burn slowly and may outlast almost everything. The color and brightness of a cluster tell you what it has already lost and what it still holds. Nebulae tell a different story. Their spectra reveal ingredients, hydrogen and helium, of course, but also oxygen, nitrogen, sulfur, and the heavier elements that planets will someday claim. In that light, you can read the periodic table as if it were written across the sky. For centuries we thought we were seeing the whole picture when we tilted our heads back at night. Stars, a few smudges, the river of the Milky Way. Then we learned to stare longer. In the mid-1990s, the Hubble Space Telescope was asked to look at almost nothing. Astronomers pointed it at a tiny, dark patch of sky, a piece of apparent emptiness, no larger than a grain of sand held at arm's length, and let it collect whatever photons would come. 10 days passed. That is a long time to devote to a blank patch. Many expected very little. The result was the Hubble Deep Field, an image that is now a small icon of wonder. There were galaxies everywhere, not stars, galaxies. Spirals with delicate arms and glowing cores. Ellipticals like golden embers. Irregular fragments that looked like smudged brush marks. Thousands of them, scattered across that tiny window. Each one a city of stars, each one likely containing its share of gas and dust, its own clusters and nebulae, its own dark halo of matter we could not see. That one image changed the scale inside our heads. If a grain of sand square of sky could hold thousands of galaxies, then the full dome above us must hold numbers that are not just large, but dizzying. We repeated the experiment with deeper exposures and better cameras, and then extrapolated. The rough estimate that emerged suggested something like 2 trillion galaxies in the observable universe. Trillion here is not a flourish. It is an attempt to put a border around the unbordered. 2 trillion islands of stars, each with their own storms, their own quiet nights, their own long arcs of birth and loss. Most of those galaxies are too faint for us to see in detail. Their light is stretched by the expansion of the universe into redder wavelengths, thinned by dust, or simply too meager to rise above our noise. They are there. We just do not have the eyes to see them clearly. The metaphor many of us reach for is a drop of ocean. Look at a single drop and you can learn something. You can taste the salt. See the tiny lives that drift within it. Measure the temperature. But no matter how carefully you examine that drop, you are not holding the sea. A deep field is like that. The frame is rich, the data generous, but the truth it points to is larger than any instrument can hold. The observable universe is not everything. It is only the sphere from which light has had time to reach us since the beginning, filtered through our tools and our patience. There is a second shift in perspective here. When you look at any deep field, you are not seeing the present. The farther a galaxy stands from us, the older the light that reaches our sensors. Some of those pinwheels and embers have already merged with neighbors, or faded, or transformed. Some may not exist in their shown forms anymore. Yet their past still arrives, photon by photon, crossing the darkness. A deep field is a time field. It collects not just distance, but age. Now comes a quiet boundary. The universe is expanding, not in the sense of things flying through space like sparks, but in the sense that space itself is stretching. Place raisins in dough, then let the dough rise, and you have a simple picture. The farther two raisins are from one another, the faster they move apart as the dough swells. In our universe, there is a distance beyond which that swelling outruns light, not because anything breaks the speed limit, but because the metric that measures distance is changing underneath everything. Past that horizon, light that leaves today will never arrive here. Those regions are forever outside our reach, not just practically, but in principle. The curtain is closing gently on parts of the stage we will never see. Inside the curtain, the numbers are still overwhelming. Galaxies come in sizes and shapes that track their histories. Small dwarfs with a few billion stars wander near larger companions, their gas stripped by tides. Great spirals display arms stitched with blue clusters and pink star-forming regions. Ellipticals glow with the older light of red stars and hold massive black holes in their cores. Some galaxies are interacting, pulling on each other's disks until they trail tidal streams like ribbons. Others pass quietly in the outskirts, too far to trouble their neighbors. Multiply any of this by the trillions, and the mind hesitates. Perhaps that is why the little list of what we can see naked-eyed feels comforting. A few thousand stars if the night is clear. The smeared oval of Andromeda, if you know where to look. From the southern hemisphere, the large and small Magellanic Clouds, which are companion galaxies to our own. All the rest is hidden until you bring glass. It is almost comedic. We live inside a sky that is saturated with galaxies, yet our senses admit only a handful. The limitation does not spoil the wonder. It heightens it. A single deep image becomes a sanctuary. A single faint smudge becomes a pilgrimage. You do not need to hold the whole to feel the weight of it. Knowing is enough to widen the chest. If our galaxy is an island, then we live in an island chain. Astronomers call it the local group, a small gravitational family that spans a few million light years. There are roughly 50 or so members, depending on how you count the faintest dwarfs. Most are fragile, irregular things, collections of stars, more than grand designs. Two giants set the tone, our Milky Way and Andromeda, also known as M31. The Milky Way may hold 200 or 300 billion stars. Andromeda likely holds more, perhaps close to 1 trillion. In a sufficiently dark sky, you can see Andromeda with your unaided eye, just a pale thumbprint. When you do, you are catching photons that began their trip more than 2 million years ago. The distance between our galaxy and Andromeda is roughly 2.5 million light years, which in galactic terms is neighborhood distance. The two are approaching one another at about 110 kilometers per second. Gravity, at this scale, is patient, and the expansion of the universe does not separate what is bound closely enough. In about 4 billion years, the two spirals will begin to merge. This will not be a crash in the way stones collide. Stars are small compared to the distances between them. Most will pass one another without contact, like fireflies in intersecting swarms. Gravity will do the mixing. Tidal forces will stretch and curl the disks. Gas will compress into new starbursts, and over time, the remnants will settle into a new, larger shape, probably an elliptical galaxy. The night skies of whatever worlds exist then will be astonishing. For now, the two giants keep their entourages. The Milky Way is orbited by dozens of dwarfs. The Large and Small Magellanic Clouds, visible from southern latitudes, are irregular satellites that loop around our galaxy on long, loose paths. The Sagittarius dwarf is being tidally shredded, its stars drawn into long streams that wrap around the Milky Way like faint silk. Andromeda has its own companions, including M32 and M110, which sit close to its disk like small boats near a bay. This is the quiet arithmetic of growth. Large galaxies assemble by accreting smaller ones, a slow recycling that leaves faint tidal signatures in the halo. Between the members of the local group stretches a very thin medium, gas measured in whispers per cubic meter, and a deeper, invisible scaffold of dark matter whose gravity knits the system together. The local group itself drifts inside a greater basin of attraction, falling toward the Virgo cluster, and beyond that, into an even larger flow that maps onto the Laniakea supercluster. The names are points on a map we can only sketch, but the pattern is clear. At every scale, gravity traces a web, collects matter into filaments and nodes, and leaves between them wide, clean voids. The universe loves contrast. It writes with light on darkness, and with emptiness on fullness. You can think of the local group as a small town at the edge of a sprawling county. The town is quiet, with slow traffic and old roads. But the highways beyond it connect to busier places. The Virgo cluster lies about 50 to 60 million light-years away, a crowded district of thousands of galaxies, and the local group's motion hints that we are not simply sitting still. We are falling, drifting, responding to tugs we infer from the motions of many neighbors at once. The map of these flows was sketched by measuring redshifts and distances, then tracing the currents like a cartographer with a patient hand. Where the currents converge, you find mass. Where they disperse, you find emptiness that is not truly empty, just spare. Inside this web, dwarf galaxies matter a great deal. They are laboratories that keep cosmic memory. Many are metal poor, meaning they have fewer heavy elements, and so preserve the conditions of early star formation. Some are tidally stirred by their hosts, their orbits elongated, their stars smeared into arcs. Others are stubborn and compact, resisting tidal stripping longer than expected. When astronomers catalog these small companions and measure their motions, they test our understanding of dark matter. The way these galaxies rotate, the shapes of their halos, and the survival of their streams all act like fingerprints of the invisible mass that binds them. Return your attention for a moment to a single deep field. The galaxies in that frame are not scattered randomly. They show hints of filaments, groups, and clusters. You can almost see the large-scale web in miniature. In richer images, arcs appear around massive clusters where gravity bends light. This gravitational lensing has become a tool. It magnifies distant galaxies and also reveals mass where no light shines. The cluster may contain as much dark matter as luminous matter, and the lensing pattern maps both. It is a quiet triumph to measure what cannot be seen by watching how it changes the path of light. All of this structure, from dwarfs to clusters to the web itself, grows from small seeds laid down in the early universe. Tiny fluctuations in density, amplified by gravity, became the scaffolds on which galaxies condensed. Gas fell into these wells, cooled, and formed stars. Feedback from those stars, along with energy from black hole accretion, stirred and heated the gas, regulating the pace of formation. The result is a balance that looks chaotic from up close and graceful from far away. The universe is not aimless. It is statistical. Given time and the right ingredients, it composes spirals and ellipses the way wind composes dunes. Andromeda's approach is a reminder that even in an expanding universe, what is bound stays bound. The merger it promises is not an apocalypse. Worlds, if they exist then, will mostly pass through unharmed. The skyline will be stranger. Tidal tales may sweep the heavens, starbursts may light up regions like festivals, and the core may evolve into a brighter, rounder heart. After the dance settles, a new galaxy will remain. One with a memory of two. Perhaps some future astronomer, speaking from a world we cannot imagine, will look up at the halo and trace the streams of ancient collisions like rivers on a continent. Meanwhile, our own night sky conceals similar stories. The Sagittarius stream wraps around us. The Magellanic Clouds are linked by a bridge of gas. The Magellanic Stream, pulled out by tides and ram pressure as they move through the Milky Way's halo. It is tempting to ask whether our place in this arrangement is meaningful, whether the Orion arm is fortunate, whether the timing is kind. The answer depends on what you value. Life on Earth has enjoyed long seasons of stability, punctuated by resets. Our position, well outside the chaotic core and not inside a starburst region, may have helped. The metallicity of our part of the disk, an astronomer's way of saying there are enough heavy elements to form rocky planets, certainly helped. The rhythm of supernova in our neighborhood mattered too. They seeded us with elements and at times shook the atmosphere. The galaxy provides the theater. The script is local. From here, when we lift our eyes, we can still see the Milky Way as a hazy bridge of light. On very dark nights, you can pick out its texture, mottled with dark lanes where dust hides distant stars. Those dark lanes are not absence. They are the raw material of future suns. In a few tens of millions of years, some of those pockets will cool enough to collapse. The cycle will continue. New stars will light, planets will accrete, and somewhere in the long arithmetic, another shore will be traced by water and wind. At the same time, the deeper future is drawing its own boundary. The expansion of the universe is accelerating, driven by what we call dark energy, a name that is a placeholder more than an explanation. As the acceleration continues, more and more distant galaxies will fall out of causal contact with us. Their present light may still be on its way, but beyond a certain distance, any new light will never arrive. The observable universe will become a quieter room. In trillions of years, if any observers remain within the merged remnant of the Milky Way and Andromeda, their sky may show only the stars of their own galaxy, with the rest of the universe's history hidden behind an event horizon of expansion. Cosmology will become local history. Archaeology of the sky will shrink to the hill you stand on. That thought is not sad. It is clarifying. It reminds us that our moment is generous. We live at a time when the sky is still full of messages from far away, when deep fields can still be crowded, when the past still finds us. We are not required to see it all to love it. We are required only to notice what we can, and to keep asking for a little more. If you prefer, think of it like walking at dusk. The street lights come on one by one. In the softening light, you see the near things first: leaves, stones, a porch. Then as your eyes settle, The farther shapes emerge: trees, rooftops, the long line of the road. The night sky trains us in the same way. First the bright stars, then the band of the Milky Way, then the faint smudge of Andromeda. Then, with help, the dim arch of a cluster or the breath of a nebula. With patience and the right tools, even the background resolves into cities of light. So our neighborhood extends from clusters and nurseries to galaxies and groups, then outward into a supercluster and the web beyond. Every step outward costs us detail, but it buys us perspective. Every step inward costs us perspective, but it buys us detail. The art is to keep both. To know that a single young star in Orion carries the same physics as 100 billion-star spiral on the edge of a deep field, and that both belong to a pattern that keeps writing itself across space and time. We are part of that writing. The hydrogen in the first nebulae became helium in the first stars, then carbon and oxygen and iron in the second and third generations. Those atoms drifted, cooled, and condensed into worlds. On at least one of those worlds, chemistry learned to copy itself, then to remember, then to wonder. Now some of that matter has learned how to name what it sees. It has learned how to hold up a mirror to a dark sky and say, "There is more." The galaxy within reach is not just Andromeda on a clear night, or the local group mapped like a family tree. It is the sense that what is far can be brought close by attention. You do not need to own a telescope to practice it. You can practice by stepping outside and letting your eyes adjust. You can practice by tracing Orion from the belt to the sword and then to the nebula you know is there. You can practice by imagining that faint smear that is a sister spiral, its own planets turning through their seasons. Attention is a kind of travel that costs no fuel. Curiosity is a kind of engine that does not run down. When we say galaxies within reach, we do not mean reachable by rockets, at least not yet. We mean reachable by mind, by patience, by the slow expansion of our shared picture. The same patience that once held a telescope on an empty patch of sky for 10 days can hold a question for 10 years or a project for a lifetime. That is how the map grows. That is how the blank places on the chart get names. And when you finally set the map aside and look up again, you may find that the feeling that first sent you searching has survived the numbers. The hush is still there. The light is still old. The brushstrokes still carry stories, somewhere far beyond what our instruments can presently resolve. Another spiral turns slowly in the dark. Whether its light will ever reach us is not the only measure of its worth. It shines. That is enough. The smallest companions are often the easiest to overlook. Dwarf galaxies slip across the background like faint smudges, their light diluted by distance and poverty of stars. Some hold only a few million suns, a rounding error by galactic standards. So they hide in our surveys until someone notices a subtle excess of stars moving together, or a faint ripple in the sky's brightness that refuses to be noise. As our instruments sharpen and our algorithms grow patient, we keep finding more of these quiet neighbors in the outskirts, each one another piece of the local puzzle. Their modesty hides an outsized importance. Many astronomers think dwarfs are the bricks from which larger galaxies were assembled. The Milky Way and Andromeda likely grew by accreting systems like these, swallowing their stars and dark matter halos and stirring their chemistry into the larger mix. You can read this history in gradients of metallicity, in tidal streams that trace ghostly arcs around the disk, and in the way satellite galaxies cluster along preferred planes. The dwarfs are not footnotes. They are chapters that fed the book. Most are old. They have been drifting for billions of years, sometimes grazing a giant and losing their gas, sometimes just orbiting in long, slow ellipses, their star formation throttled by time and environment. Long before Earth formed, the local group already had its small-town politics. Long after our oceans are gone, the same families will still be circling, quietly merging, quietly glowing. It is tempting to jump straight to the grand architecture of the universe, to the filaments and walls and the deep scaffold that spans billions of light years. But there is value in starting here, close to home. The local group is not a metropolis. It is a scattered village of about 50 galaxies, give or take, with 2 bright spirals setting the tone and a collection of dwarfs keeping company around them. Distances are great enough that you can feel the solitude. They are small enough that you can feel the kinship. When you look up, every point of light belongs to some larger neighborhood, some gently shared motion. There is comfort in knowing we are not entirely alone. If galaxies are cities, then superclusters are continents. Here the scale steps up again. Thousands of galaxies gather into clusters, and clusters gather into larger associations whose outlines only become clear when you zoom far out and let statistics, not eyesight, do the work. Our local group rides inside a larger flow called Laniakea, a Hawaiian word that means immense heaven. It is an apt name. Laniakea spans more than 500 million light-years and contains over 100,000 galaxies. Light itself would need 500 million years to cross from one margin to the other, and yet Laniakea is only one province in a greater map. That greater map is the cosmic web. When you simulate structure formation in a computer and set gravity loose on tiny fluctuations in the early matter field, what emerges looks like a 3-dimensional lacework. Dense nodes form clusters. Clusters link by filaments. Between them lie vast, dark voids where almost nothing shines. These voids are not mistakes. They are part of the composition. Their emptiness defines the brightness of the walls around them, like ink that gives shape to calligraphy. This web did not appear suddenly. In the beginning, small differences in density were seeded by physics we are still learning to name. Gravity amplified those differences. Slightly heavy regions grew heavier, gathering gas and dark matter into filaments that thickened with time. Slightly light regions drained and expanded into clean basins. The process is fractal-like in spirit. Zoom in and you see groups within clusters. Zoom out and you see clusters within superclusters. The pattern does not repeat exactly, but it rhymes. Every few years, we push the limit of what we can chart. In 2003, the Sloan Great Wall was mapped, a structure more than 1 billion light-years long. Later catalogs suggested even larger walls, like Hercules' Corona Borealis, and with each discovery, we were reminded that the universe is willing to be more extravagant than our last guess. Yet all these are still inside the observable sphere. There may be webs beyond our horizon that our light will never touch. From our seat in the disk of the Milky Way, these scales can feel abstract. But we have learned to make 3-dimensional maps by measuring redshifts and distances for hundreds of thousands of galaxies. When you plot them in space, the picture snaps into view. Chains of galaxies hang like beads. Voids bloom like black bubbles. The luminous matter traces a skeleton that belongs to something heavier and unseen. Most of the mass is dark matter. We do not see it directly, but we feel its pull in rotation curves, in velocity dispersions, and in the way gravity bends the path of light. The web, in that sense, is a backlit X-ray. What glows outlines what does not. There is a limit to all this zooming. Go far enough, and detail gives way to averages. Individual galaxies blur to dots. Dots blend into a smooth field that is statistically uniform. This is the cosmological principle. On sufficiently large scales, the universe looks the same in every direction. It is not featureless so much as balanced. Texture yields to equilibrium. Still, while the web is grand, it is not separate from us. We are woven into it. The calcium in your bones and the iron in your blood were cooked in stars that belong to some earlier branch of the same network. Every galaxy is a droplet that rides the same filaments, pulled along by the same deep gradients set long ago. There is humility in that thought. There is also belonging. The visible horizon places a practical frame around our curiosity. The observable universe spans about 93 billion light-years across. This is not a wall, it is a time limit drawn by light speed and the age of the cosmos. Because space has expanded since the first photons left their sources, the galaxies whose ancient light we catch now are, at present, more than 46 billion light-years away. Double that for diameter, and you get our working bubble. Light takes time. Our instincts were built to handle ladders and streets, not a metric that stretches like warm taffy. But the numbers check out, and the sky agrees. The most distant smudges we can detect were already old when Earth was new. Many are so redshifted that their light is barely within reach of our detectors. Beyond them, the darkness is not empty. It is simply unarrived. There is a further boundary called the cosmological event horizon. Because the expansion is accelerating, some regions are receding from us so quickly that light emitted there today will never reach us. No amount of waiting will help. Those places are real. They have their own galaxies and their own nights. But their messages are forever sealed from us by the way the metric evolves. The universe is generous with what it reveals. It is also firm about what it withholds. Remember that the observable universe is always centered on the observer. That does not make us special. It is simply how light cones work. An astronomer in a distant galaxy would measure a similar radius around themselves, with a different outer fringe and a different set of unreachables. Observation is local. Reality is not offended by that. Inside our sphere, we have learned a great deal. We chart clusters and filaments, watch supernova in distant pasts, and catch quasars blazing from the youth of galaxies. We listen to the afterglow of the beginning, the cosmic microwave background, which comes from a time about 380,000 years after the Big Bang. In that thin static lies a fingerprint of the first fluctuations that later grew into the web. We measure the expansion rate, weigh the dark matter and dark energy in sums that feel more like poetry than finance, and compare maps from light with maps from lensing to test whether our invisible scaffold is drawn correctly. And yet, limits remain. Past a certain redshift, signals melt into noise. Dust veils some lines of sight. Time itself blocks others. The questions do not stop at those margins. They simply change shape. If we cannot see beyond the horizon, does it still count? Most cosmologists answer yes. The laws that hold here do not vanish there. The universe almost certainly continues. It may be infinite. It may curve. It may contain regions with histories that rhyme with ours and regions that do not. For now, we work with what we have, which is already abundant. What we have is enough to keep wonder busy. The sky we share contains the fingerprints of time, the scaffolding of structure, and the echoes of light that left before our species had words. It also contains a quiet invitation. To look is to participate. To measure is to join the rhythm. To imagine is to cross distances we cannot yet travel. There is comfort in knowing that even at limits we can still move. Not outward with ships, perhaps, but inward with patience. The same habits that built a deep field image out of a dark square of sky can build a map out of 1,000,000 measured redshifts, and a theory out of 1,000 careful disagreements. When observations and models argue, the argument is fertile. It points to a missing ingredient or an incorrect assumption. The universe uses our errors to tutor us. Closer to home, the dwarfs continue to teach. Their orbits, shapes, and star formation histories carry the signature of dark matter. Their survival against tides tests how cuspy or chord their halos are. Streams peeled from them sketch faint rings in the Milky Way's halo, and give us a ruler to measure our own potential. When we add in the Magellanic Clouds and their gaseous bridge, the picture acquires motion. You can almost see the traffic around our disk, the give and take of mass and momentum that slowly fattens a galaxy. Lift your eyes and the Milky Way itself becomes a bridge across the sky. The dark lanes you notice on a truly clear night are not absences. They are reserves. Cold gas and dust await their turn. Given a few tens of millions of years, pockets will compress, gravity will thread the needle, and new stars will flicker on. Around them, disks will gather. In those disks, pebbles will collide, stick, and grow. Somewhere, water will learn a shoreline. The cycle continues because the universe likes to recycle. Beyond our group, the map connects to Virgo, then to Laniakea, then to the broader web. Our motion through this web is not dramatic to the eye, but it is measurable. We are falling gently along gradients carved by mass we cannot see directly. Peculiar velocities add to the smooth Hubble flow. On these scales, the song is low and slow. Gravity hums a bass line that has been playing since the first bar. The further future writes its own coda. As dark energy continues to dominate, more distant structures will slip beyond communication. The local future, however, grows denser. The Milky Way and Andromeda will approach and merge in a few billion years. Tidal tails will trace loops in the sky. New stars will spark where gas is squeezed. After the dance, an elliptical remnant will shine with the combined memory of two disks and their satellites. In that era, any remaining observers may see a simpler sky. The deep field will be local. Cosmology will look like history. The evidence for expansion and for the web beyond will be embedded in fossils. Aging star populations, black hole demographics, stellar streams frozen in a puffier halo. That imagined austerity does not make our moment fragile. It makes it luminous. We are alive in a time when the sky is crowded with messages from far away. When our detectors still gather photons from the first galaxies. When the microwave background still prints its faint modeling across the whole dome. The luxury of evidence is a kind of weather. We live in good weather. The language of structure is always a trade between detail and context. Go inward and the details multiply. Cluster color magnitude diagrams, nebular emission lines, star-forming knots in dusty arms. Go outward and context clarifies the group, the cluster, the filament, the void. To understand, you learn to breathe both ways. The Orion Nebula is a nearby nursery where gravity is writing birth certificates in hydrogen light. The Virgo cluster is a crowded square where galaxies elbow for space, and intracluster gas glows in X-rays. The Sloan Great Wall is a sentence in a paragraph that stretches across 1 billion light-years. Each scale completes the others. In this layered view, nothing is lonely. A dwarf galaxy that seems meager still carries a lineage. Its stars bear chemical ratios that recall earlier supernova. Its orbit remembers past tides. Its gas knows the pressure of the medium it moves through. A nebula that looks like a veil is a kiln. The filaments that look like strokes of chalk are highways. The voids that look like nothing are frames that make the picture legible. If you step outside on a clear night, give your eyes the time they need. The bright stars arrive first, then the band of the Milky Way, then the thicker knots. If you know where to look, you can tease out Andromeda as a soft blur. Everything else needs help. That is fine. A telescope is a kind of patience made of glass and alignment. A survey is a kind of patience made of repetition. A simulation is a kind of patience made of math. All of them are ways of lengthening attention until the sky reveals another layer. In the end, this chapter is not only about cataloging structures, but about learning how to belong to them. You belong to a star that belongs to a spiral, that belongs to a group, that belongs to a flow, that belongs to a web. The web belongs to a history that began in simplicity and unfolded into complexity. A history that left room for water and trees and conversations under a night sky that still holds more messages than we have yet learned to read. If that realization makes you feel small, let it also make you feel placed. Small and placed is a good way to be in a universe like this. The distances are enormous. The numbers are stern. But the act of looking is intimate. The act of understanding is local. You stand on a planet, and you breathe air made by ancient oceans and forests, and you look up, and photons that left other worlds before names existed encounter your eyes and are finally spent. That meeting is not statistical. It is specific. It is yours. So we go on. We map the dwarfs and their streams. We register the clusters and their histories. We trace the filaments and weigh the voids. We look for the next faint signature and ask if our model is generous enough to hold it. And as we do, the feeling that first drew us outside returns. The hush is still there. The brushstrokes are still visible. Somewhere, not far in the language of the web, a small galaxy is being taken in by a larger one, and the stars it gives will shine in a new home. Somewhere, very far in any language, another spiral turns in a darkness that is not empty. Whether its light reaches us is no measure of its worth. It shines. That is enough.
The edge we speak about is not the edge of reality, only the edge of our sight. It is a soft horizon that glows with ancient light, always receding, always just beyond the grasp of the present. Not a wall, not a curtain in space. It is a limit set by time and by the speed of light, a reminder of how far photons can travel, and how far our curiosity has stretched to meet them. Around us, there is a horizon built of time and light, a roundness drawn not by clouds, but by the ages. Beyond it, the messages have not arrived. Within this boundary lies what we call the observable universe, a sphere that reaches roughly 46 billion light-years in every direction, when measured by where those distant sources are now. It sounds contradictory at first. If the universe is about 13.8 billion years old, how can the observable radius be more than 13.8 billion light-years? The answer lives in the expansion of space itself. While the light was in flight, the fabric of space lengthened. So the sources are now much farther away than they were when their photons began the journey. The light is old, the distance has grown, and the numbers make peace once you let time and geometry speak together. What lies beyond that horizon is a question that belongs both to physics and to humility. If we can only observe what has had time to reach us, then the unobserved may be vast beyond telling. It is not a blank. It is only out of reach. To understand why the horizon exists at all, we have to begin near the beginning. In a sliver of time just after the Big Bang, the universe went through a period called cosmic inflation. This was not a gentle swelling. It was a blisteringly fast expansion that took tiny quantum ripples and stretched them across cosmic scales in less than a heartbeat. In a fraction of a second, space grew so quickly that regions once in causal contact were hurled apart. When inflation ended, those ripples remained as slight over and under densities, a softly speckled blueprint that gravity would later amplify into the cosmic web. The filaments and nodes that would seed galaxies and clusters. Inflation had side benefits. It explained why the universe looks so smooth on the largest scales, why its curvature appears so close to flat, and why the temperature of the early light is nearly the same no matter where we look. The mathematics is subtle, but the picture is friendly. Take a small, nearly uniform patch and stretch it to enormous size. Any wrinkles become gentle, any bends flatten out. The leftover freckles are precisely the sort of seeds gravity loves to work with. As the hot plasma cooled, a remarkable transition occurred. About 380,000 years after the beginning, electrons coupled with protons to form neutral hydrogen. Light that had been scattered constantly by free electrons could suddenly travel largely unimpeded. The universe became transparent. The glow from that moment still surrounds us. We call it the cosmic microwave background, the oldest light we can see. It is not the oldest thing. It is simply the oldest light that can reach us, a snapshot of the universe as a newborn. Look closely at that glow, and you find faint temperature ripples. Tiny variations, a few parts in 100,000. Those ripples map directly onto the density fluctuations that inflation stretched and gravity later deepened. They are fingerprints from the nursery, hints of the skeleton the cosmos would grow into. But every galaxy you have ever seen is a consequence of those small differences written on a hot sky that no longer exists. Beyond that glow lies darkness in the literal sense. Not absence, only silence. Light from beyond that era either has not yet arrived or has been redshifted into energies we cannot capture with current instruments. The horizon, in this view, is a time limit that shapes our field of view. Some messages are still on the road. Some will never find us, because the road itself is stretching faster than they can cross it. Imagine standing on a shore while mist thickens over distant water. You know the sea continues. You cannot see the ships at that distance. The fact of their invisibility is not an argument against their existence. So what is out there? One simple possibility is that the universe continues much as it does here. More galaxies, more clusters, more filaments, more voids, an extended quilt of matter and energy. If physics is universal, there is no reason to suppose our region is more special than any other. The unobservable may be unimaginably large and also surprisingly familiar. Many cosmologists take a deeper step
and suggest that the universe is either incredibly large or truly infinite. If so, our observable bubble would be one patch in an ocean without shores. You could sail in a straight line forever and never meet a wall, only new water. In an infinite cosmos, repetition becomes not mystical, but statistical. Given enough space and enough random arrangements within the same rules, patterns recur. It is a strange delight to imagine that very far away, there could be another patch statistically identical to this one. Not because of magic, but because of combinatorics. The distances involved are so absurd that the idea is safe from becoming mundane. There are more adventurous possibilities. Some models of inflation suggest that it never ended everywhere, only in pockets. Our observable universe would then be a bubble that cooled and formed galaxies, while other bubbles continued to form elsewhere, each with its own physical constants, its own particle content, perhaps even a different number of spatial dimensions. This idea, sometimes called eternal inflation, paints a multiverse that is more like a froth than a single balloon. It is mathematically coherent, and certain versions flow naturally from the same equations that work so well elsewhere. It is also very difficult to test. By definition, other bubbles would be causally disconnected from ours. We can seek indirect hints at their existence. We can look for scars that a bubble collision might leave on the microwave background. But the door may never open far enough to confirm or deny. The question is real, even if the access is limited. Uncertainty has value. It protects us from mistaking a map for the territory. We have come far from the first recognition that the sky contains other galaxies, to painstaking measurements of the early glow and the large-scale web. Yet there will always be more past the edge of the last contour line. The unobservable is not an embarrassment. It is a natural feature of a universe where light has a finite speed, and the clock has only been ticking for so long. Even within our observable sphere, the expansion of space plants a second horizon. Because the expansion is accelerating, driven by whatever we label dark energy, there exists a distance beyond which light emitted today will never reach us. Not a speed violation. Nothing outruns light locally. Rather, the very measure of distance grows so quickly that the gap increases faster than photons can bridge it. The result is a cosmological event horizon, a boundary in time, beyond which messages are forever undeliverable. Within our globe, we have learned to read light very well. We build telescopes and place them above the blur of air. We stare for hours, days, weeks, and sum the trickle of photons into a single deep image. Piece by piece, we assemble a coherent picture in which the same parameters make sense of multiple, independent clues. The expansion rate, the matter content, the geometry, the growth of structure, the checks tied to each other. And where they disagree, we listen closely. Because disagreement is often the place where the next lesson lives. There is a more philosophical question that lurks near the horizon. If we cannot observe beyond it, should we speak about what lies there? Does it count? The usual answer is modest. We assume that the same laws apply beyond our reach unless there is a strong reason to think otherwise. This approach has served science well. It is not dogma. It is a practical bet that nature is of one piece. If the bet fails, the failure itself will be a discovery. Until then, continuity is a sensible default. For now, our observable bubble is generous. It contains the glow from the first transparent moment.
the light from infant galaxies, the arcs that massive clusters draw by bending light, the burst of supernovae that act as standard candles across billions of light years, and the faint whisper of hydrogen clouds that sing at radio wavelengths. It contains filaments strung over hundreds of millions of light years and voids that are nearly empty. It contains the raw material required to weigh the invisible mass we call dark matter and to see the fingerprints of dark energy on the growth of structure. And it contains a lesson about wonder that is worth holding on to. Knowledge does not shrink the sky, it deepens it. Learning that we see only a slice does not make the slice smaller. It gives its edges meaning. To know there is a horizon, to know why it exists, is to feel placed rather than diminished. You are standing at a shore where light laps and whispers of things beyond. The whisper is not silence, it is an invitation. The practical corollary to all of this is patience. Some light has not arrived yet. Some instruments have not been built. Some patterns are just beginning to emerge. For now, we keep looking. We keep building better clocks and better glass. We keep comparing maps that were made with different kinds of light to see if they agree about the same terrain. We keep asking whether inflation left marks we have not yet learned to read, and whether the acceleration of the universe tells us something profound about the vacuum itself. The horizon will recede as our instruments improve, but some parts will always remain out of reach. That is not a failure. That is the kind of world we live in. And even if parts of the cosmos will always be hidden, remember this much. Everything we do see, every deep field, every spectrum, every tiny shift in the glow of the first light has crossed a universe to meet us. Those photons are ancient travelers. They have ridden the expansion, stretched and reddened, lapped by the tides of time, yet still coherent enough to carry information. When they land on a detector or on the back of your eye, the journey ends. And in that moment, a very old story becomes present tense. The edge of sight is not where the story stops. It is where the next question begins. At first glance, it is easy to imagine galaxies as separate ships making their way across a dark ocean. This one turns a little, that one drifts away. Here a cluster gathers like a convoy. The picture is appealing, but it misses the heart of the matter. Galaxies are not simply moving through a fixed emptiness. The emptiness is not fixed. Space itself is stretching, which means the distances grow, not because the ships are rowing, but because the sea is swelling everywhere at once. The modern story began a century ago with careful measurements of light from the faint smudges we now know are other galaxies. These spectra showed prominent features shifted toward the red. The wavelengths lengthened compared with the same features measured in a laboratory. Edwin Hubble, building on earlier work by Henrietta Leavitt, Vesto Slipher, and others, collected distances and redshifts and found a pattern. The farther a galaxy was, the stronger its redshift, and the speed inferred from that shift was roughly proportional to the distance. This linear relation is now called Hubble's law. It told us the universe is expanding. At first, many described this as galaxies flying apart through space. Over time, a better picture took hold. It is space that expands, carrying galaxies with it. The analogy of raisins in rising bread is useful. The raisins do not sprint. The dough grows and increases the gap between them. The farther apart two raisins are, the faster their separation increases. The same is true in our universe. On large scales, the Hubble flow carries galaxies apart because new space keeps appearing between them. This model leads to effects that are both strange and beautiful.
Distant light is stretched while it travels, which shifts it toward redder colors. That reddening can be caused by motion in the usual sense, but for very distant galaxies, it is primarily caused by the growth of space itself. The technical term is cosmological redshift.
Light is a wave, and as the ocean beneath it expands, the crests drift farther apart.
We have learned to turn this stretching into a ruler and a clock. Supernova of a particular type act like standard candles, letting us estimate distances from their brightness. Spectral features let us measure redshift. When these two are plotted against each other for faraway galaxies, the line they draw is not what it would be if the expansion had always been slowing. In the late 1990s, two teams found that the expansion had begun to accelerate in the recent cosmic past. Something that behaves like a uniform energy density is driving the acceleration. We call it dark energy.
The name is a label, not an explanation.
We see the consequence in the way structures
Grow more slowly than gravity alone would dictate, and in the way distant supernova appear dimmer than expected.
This acceleration creates a subtle kind of isolation. Galaxies that are not gravitationally bound to us
will continue to recede, and many will eventually slip beyond our event horizon. Their light emitted today will never be seen here.
They will still exist, but for practical purposes,
They are removed from our future sky. It is a gentle loss. No object disappears from the present view. Rather,
future messages never arrive.
the cosmos becomes very slowly a quieter room. There is a companion fact that makes the picture less bleak.
Expansion does not tear apart everything.
Gravity and other forces easily hold small scales together. The Milky Way is not expanding. Your body is not expanding. Even the local group resists the Hubble flow. Our galaxy and Andromeda are on a slow collision course that will take a few billion years to unfold. After close passes draw out tidal tails and trigger starbursts, the two will settle into a larger, rounder system. The rising dough does not separate raisins that have already baked into the same bun.
The darkness of the night sky,
An old puzzle, sometimes called Olber's paradox, also finds a graceful answer in this framework. If the universe were static and infinite and eternal, the sky should blaze with starlight from every direction. Instead, it is dark. The reasons are several. The universe has a finite age, so not all the light that could exist has arrived.
space expands,
which redshifts and dims distant light.
Stars are not packed
Uniformly across space or time.
We live under a sky
Where absence has structure and where distance at its brightness.
redshift itself is a storyteller.
When a galaxy is near and coming toward us, its light shifts slightly blue. When it is far and receding, its light shifts red. For the most distant sources we can see, especially the earliest galaxies and quasars, the light has been stretched by factors of 10 or more, moving ultraviolet starlight into the infrared and visible wavelengths into microwaves.
The microwave background is an extreme example of this.
What began as a fierce, brilliant glow when the universe first became transparent has been stretched across 13.8 billion years until it has the spectrum of a cold, nearly uniform microwave bath. It is ancient light, softened by time.
As we pair observations with models, we have learned to speak carefully about distance. There is co-moving distance, which factors out the expansion so that fixed points in the cosmic web
remain at fixed coordinates. There is light travel time, which reports how long a photon has been en route. There is angular diameter distance, which tells us how big something appears, and luminosity distance, which tells us how bright it seems. These are not pedantic distinctions. The shapes of the curves they draw against redshift encode the expansion history, and from that history, we infer the density of matter and the character of dark energy. A single graph can be a conversation between light and geometry. The expansion leads to a future that is both elegant and a little austere. Given enough time, most galaxies will fade from view. Their light will be stretched beyond detection. Their presence betrayed only indirectly in the structure they helped form long ago. The sky will look more local. The deep field will narrow to the neighborhood. If any astronomers live in that distant era, their cosmology will be harder to reconstruct because the evidence we see now will have thinned. Our time is fortunate. We can still capture ancient photons in our instruments, still measure the web beyond our group, still read the background glow as if it were a parchment in the archives. It is worth emphasizing that none of this robs the universe of its intimacy. If anything, it hands intimacy back to us. Every photon a telescope collects is an individual traveler. Each carries a phase and an energy and a direction. Each has crossed gulfs widened by expansion and yet arrives with enough clarity for us to read chemistry and temperature and motion from it. We use prisms and gratings to unfold a spectrum and then turn those lines into history. There is something moving in that translation. Light, which began as an event in a place we will never stand, lands here and becomes comprehension. At the human scale, the expansion is invisible. No room grows overnight. No orbit loosens between dawn and dusk. Yet the gentle stretch writes the larger story. Clusters are more isolated than they were. Filaments lengthen, voids widen. The web relaxes at the edges. The speed limit that light imposes and the acceleration that dark energy supplies collaborate to make a cosmos where stories become local over unimaginable spans of time. If this feels unsettling, try a different reading. The universe is making room. Room for time to pass. Room for complexity to arise and then to rest. Room for galaxies to breathe, for stars to live out their fuel, for planets to try chemistry for a while. Expansion is not escape. It is allowance. It gives us the distance needed to notice. And in the end, we are still connected by the very thing that draws the horizon around us. Light is our messenger. It is also our measure. It tells us where and when, not just what. When a photon leaves a galaxy, its wave crests are a certain distance apart. Over billions of years, those crests are pulled wider by a universe that keeps growing. And by the time the photon touches a detector, its color has shifted. We can look at that shift and reconstruct the path. We can use it to weigh what cannot be seen and to time what cannot be repeated. We can join our brief present to an enormous past. So we look up and we keep looking. We accept that some edges will remain edges, that some questions will live at the boundary between inference and proof. We also accept that this is not a failure, only a kind of weather. On clear nights, the dome is crowded with messages. On cloudy nights, we wait. The horizon is there either way, a roundness defined by what has arrived. Beyond it, the story continues. Within it, there is enough to wonder at for as long as wondering is possible. Redshift is not just a quirk of light, it is a ruler and a timepiece in one. As space stretches, a photon's crests drift farther apart, so its color slides to longer wavelengths. What began as a vivid blue can arrive as a soft red, or as invisible infrared, or even as radio. That change is the measurable record of the journey. By splitting a galaxy's light into a spectrum, we can read how much stretching has occurred, then infer both distance and look-back time. In practice, every distant glow is a message from the past. Andromeda's light needs more than 2 million years to reach us, so the smudge you see on a dark night is truly ancient. Push farther, and the clock winds further back. A galaxy 10 billion light-years away shows us itself as it was 10 billion years ago. The universe offers us a time-lapse in reverse, written in color. Redshift carries deeper meaning than distance alone. In the 1920s, careful measurements linked greater redshifts to greater distances, which implied a consistent pattern of recession. It was not that we occupied a privileged center with everything fleeing that center. Rather, the pattern looked the same from any galaxy's vantage point. The only simple explanation was that space itself expands. Think of raisins in rising bread. The raisins do not sprint across the dough. The dough grows, and the gaps between raisins widen. On very large scales, that is what the cosmos does. As the fabric stretches, wavelengths stretch with it, and distant light arrives redder than when it began. Once you admit cosmic expansion, a beginning comes into focus. If distances are increasing today, then yesterday they were smaller. Run the film backward, and you reach an early time when matter and radiation crowded into a hot, dense state. The Big Bang is that limit of extrapolation, not an explosion inside space, but the birth of space and time as they expand. The early universe was not spacious. It was tiny and fiercely hot, a seething plasma where familiar particles struggled to exist for long. Within a whisper of a second, something even stranger likely occurred. A brief episode called inflation appears to have expanded space incredibly quickly. Inflation is not matter outracing light. The speed limit applies locally. It is the geometry itself increasing in size, which does not break the rules. Inflation took quantum jitters and magnified them, freezing small ripples into slightly over and under dense regions. Those ripples were the seeds. Gravity would later amplify them into the large-scale web of filaments and nodes that hold galaxies and clusters today. A few minutes into the story, the sea of free protons and neutrons cooled enough to fuse into the first simple nuclei, mostly hydrogen with some helium and a trace of lithium. Yet the cosmos remained a blinding fog, because free electrons scattered light at every turn. Only after about 380,000 years did temperatures fall enough for electrons to settle into orbits around nuclei, forming neutral atoms. The fog cleared. Photons that had been caged began to stream freely. That first free light still surrounds us as a thin microwave glow. We call it the cosmic microwave background. Look closely at this ancient afterglow, and you find faint mottling. Temperature variations only tens of microkelvin in size. Those ripples encode the original seeds left by inflation and the sound waves that rang through the early plasma. They are the baby pictures of structure formation. From that transparent dawn, gravity had time to work. Dark matter, which feels gravity but not light, pooled into halos. Gas fell in, cooled, and formed the first stars and galaxies. The earliest galaxies are faint and far. Their light stretched into the infrared. This is why a telescope tuned to infrared wavelengths such as the James Webb Space Telescope, is so effective at finding them. By catching that highly redshifted glow, we glimpse a universe only a few 100 million years old, a time when the first galaxies were assembling and reionizing the fog of hydrogen that lay between them. Redshift also reveals a quieter melancholy, because expansion is accelerating, driven by something we call dark energy. More and more distant light is stretched beyond our detectors. Future photons from many galaxies will never arrive at all. They lie beyond a cosmological event horizon, set by the accelerating growth of space. Nothing locally outruns light, yet the metric itself can separate us from messages that start too far away. Over unimaginable spans, the sky thins. Many galaxies will fade from view. Not through destruction, but because their signals are diluted and shifted into silence. Our present is fortunate. We can still gather the ancient trickle and turn it into history. It is important to keep scale in its place. Expansion does not tear apart bound systems. Gravity and other forces hold small structures together. Your body does not expand. Planetary orbits do not inflate. Galaxies remain coherent, and even small groups of galaxies, like our local group, resist the Hubble flow. In a few billion years, the Milky Way and Andromeda will meet and merge. Tidal forces will draw out long streamers of stars. New bursts of star formation will flare, and a larger, rounder remnant will eventually settle. The rising dough does not separate raisins that have already baked into the same loaf. The darkness of the night sky itself, a puzzle known historically as Olber's paradox, finds a natural answer in this framework. If the universe were static, infinite, and eternal, every line of sight would end on a star and the sky would blaze. Instead, it is dark because the universe has a finite age, because space expands and redshifts distant light, and because luminous matter is patchy in both space and time. The dark is not a lack of stars. It is a consequence of history and geometry. The language of distance needs care, and redshift is how we keep that care. There is co-moving distance, which factors out expansion to keep coordinates fixed on the growing web. There is light travel time, which is simply how long the photon was on the road. There are angular diameter and luminosity distances, which turn apparent size and brightness into measures that can be plotted against redshift. The shapes of those plots encode the expansion history. From that history, we infer the matter density, the geometry of space on large scales, and the behavior of the dark energy that drives acceleration. A single curve can be a conversation between light and the growth of the cosmos. Redshift is also a census taker. From spectral lines, we read chemical fingerprints, temperatures, motions within galaxies, the presence of outflows or inflows, and the rate at which stars are forming. At high redshift, we see galaxies that are smaller and more chaotic than mature spirals today. We see quasars, powered by young, ravenous black holes in early galaxies, whose brilliant accretion disks shine across the universe. We see that structure grows bottom up. Small halos form first, then merge into larger ones. The web sharpens with time. The early universe timeline is now sketched with surprising confidence, although key mysteries remain. After inflation and the formation of light nuclei, there is a long age of darkness before the first stars ignite. When those first stars form, they are likely massive and short-lived. Their light and their explosions begin to reionize the hydrogen between galaxies. Over a few 100 million years, the fog lifts. Galaxies proliferate. By redshift values of a few,
The cosmic star formation rate climbs toward a peak, then declines slowly as gas is consumed or heated, and as structure formation shifts from building to refining. At the highest redshifts that we can reach, the redshift values are so large that visible and ultraviolet light is shifted into the infrared. This is why infrared observatories are our time machines to the first billion years. At the lowest redshifts, quite nearby, we can inspect galaxies in exquisite detail, map their rotation, weigh their dark matter halos, and track how their stellar populations age. Between the two extremes, we stitch a continuous narrative of growth, quenching, and transformation. Redshift is the index that keeps the chapters in order.
All of this sits inside a larger question about size and shape. Geometry on the grandest scales appears very close to flat, according to careful measurements of the cosmic microwave background and of how galaxies cluster. Flat does not require infinity, although it permits it. An open universe curves like a saddle and expands forever. A closed universe curves like a sphere and can be finite yet unbounded. You can travel without finding an edge, though you could eventually return to your starting line after an impossible journey. Current data favor a nearly flat geometry with an accelerating expansion. In that setting, there is no physical border out in space. There is a practical boundary defined by time. The observable universe is a sphere, about 46 billion light-years in radius, centered on us only because we are the ones observing. An observer in a distant galaxy would center their own sphere around themselves, with broad overlap yet different edges. There is a human note under all the numbers. Each photon that lands in a detector has crossed a universe that has been growing the entire time. It has been reddened and slowed in energy, yet remains coherent enough to carry information. In your eye, or in a mirror of glass and metal, the journey ends. For a tiny moment, the past becomes present. Redshift, in that sense, is more than a measurement. It is a language that the sky uses to tell us when things happened and how the stage itself has changed while the actors moved. It is the grammar of a universe in motion. The future will be quieter in certain ways. As acceleration continues, more distant structures will slip beyond any chance of sending new light to us. Far ahead, astronomers may see only the merged remnant of our local group and the faint afterglow of long-dead stars inside it. Their cosmology will be harder. The evidence we find so abundant today will be hidden from them by time. That does not make our moment grander than theirs, only different. We are favored with a crowded sky. They may be favored with depth of local understanding that comes from patience we can barely imagine. For now, Redshift is still a generous teacher. It lets us watch the young universe learn to shine. It weighs invisible matter and times the growth of structure. It points to a beginning and invites questions about what came before, if before even makes sense. It warns us that some messages will never arrive, which is not a failure of curiosity, only a property of the world. Most of all, it reminds us that every view is already a memory. What we see is gone in one sense and present in another, carried to us by waves that the universe has gently pulled longer. The stretch is the story, the color is the clock, and the night, when you let your eyes adjust, is a library of very old pages still drifting down.